We're going to talk today about plane wave incidence on a boundary between two materials when the wave is, excuse me, not normally incident on the boundary. So if this is the boundary, this is the interface, and the surface normal vector n hat is right here, then instead of being parallel to the surface normal vector, the incident wave's propagation vector points at some angle theta I, like that, to the surface normal. So Ki would look like this. I'm not going to draw the fields on right now because polarization is important in this sort of a problem and it changes how the solution works out. And right now I want to just talk about the propagation vectors and the direction of everything. Now, just like a normal incidence problem, you have a reflected wave, which comes out at an angle theta r. And it's got a wave vector kr, like that. And you have a transmitted wave, which comes out at some angle theta t, and it has a wave vector kt, like that. It's important at this point to talk about what the types of polarization are and what they are defined relative to. Now, right now, in general, for problems like this, we like to talk about the plane of incidence. Which is the plane that contains all of the k vectors, all the wave vectors, and the surface normal. That's the plane of incidence. So in general, it is the page or the screen. When we're talking about the polarization of problems like this, what we're referring to is the orientation of the electric field vector relative to the plane of incidence. So parallel polarization means that the electric field vector lies in the plane of incidence. And perpendicular polarization means that the electric field vector is perpendicular to the plane of incidence. Now, it's easy to get confused about this, and it used to confuse me too, because I always thought the plane of incidence meant the plane of the interface between the two materials. But the plane of incidence is the page. It is the plane that contains all the wave vectors and the surface normal vector. So if you keep that straight, the polarization stuff will never confuse you. So we're going to talk about these problems, and what we're going to talk about first is the idea of what are the values of these angles of reflection and transmission, and where do those values come from? You might be familiar with this because it is known as Snell's law. If I draw my problem again, I have my interface. I have medium 1, medium 2. For now, we're going to ignore the mu's because usually we're just talking about the dielectric constants here. And we've got some angle of incidence, some angle of reflection, some angle of transmission, and we've got the wave vectors to go with them. So that's kt, kr, and ki. Now, the one other thing that I need in order to talk about this problem understandably is I need to define a coordinate system. So I'm going to define this dotted line here as the z-axis. That's going to be the z-axis. And I'm going to say that the interface, the slice of the interface that we're looking at here is the x-axis. So that would mean that in case we care about it, the y-axis is out of the page. Based on this stuff, I can write expressions for the electric field for each of these waves. So I can say that in medium 1, electric field in medium 1, the total field, is equal to the incident electric field plus the reflected electric field. And although I don't know the vector directions of those electric fields, I do know their phase dependence because they're plane waves and I know their wave vectors. So I'm going to say E naught I is the vector direction, sort of the polarization and amplitude information about that incident wave. And then it is going to be e to the minus j ki, the vector, dot r, that's the position vector. And then I'm going to write the same sort of format for the reflected wave, E naught r times e to the minus j k sub r dot r, the position vector. Now, what are the vector components of these wave vectors? Ki is equal to k1 times some directions that are determined by theta I. So it's going to have a z component and an x component. The x component is going to be x hat sine theta I, and the z component is going to be z hat cosine theta I. Kr is going to have the same magnitude because it's still in medium 1, so it's got k1. If you remember, k1 is going to be omega times the square root of mu1 epsilon 1. And then kr is going to have opposite z dependence. It's going to point in the negative z direction, and then it's going to point in the positive x direction. So it's x hat sine theta r minus z hat cosine theta r. So far, so good. I can write a similar thing for the field in medium 2. The field in medium 2 is just the transmitted wave. So it's the amplitude and polarization information about that transmitted wave times e to the minus j kt dot r. The propagation vector for the transmitted wave is going to have a similar format. It's going to have a positive x component and a positive z component. So it's going to be x hat sine theta t plus z hat cosine theta t. But how do we find out the relationships between all of these different angles? That's the question that we're trying to answer right now. And the wave vector in medium 2 is same frequency omega mu 2 epsilon 2. What we do now is we find the relationship between all of these angles based on the boundary conditions at the interface. What we know is that the tangential components of these electric fields have to be equal to each other. Now, these electric fields may have components that are not tangential. That's okay, because when we evaluate this, if we write it in terms of the expressions we came up with for the electric field before, we end up with n hat cross E naught t times e to the, by applying this boundary condition, we find that n hat cross E naught t times e to the minus j k2 x sine theta t plus z cosine theta t must be equal to n hat cross E naught I e to the minus j k1 x sine theta I plus z cosine theta I plus n hat cross E naught r e to the minus j k1 x hat, sorry, not x hat, just regular x, x sine theta r minus z cosine theta r. Here's the trick, though. All these things need to be evaluated at the interface. So this is being evaluated at the location z equals 0. Then what we find is some constant vector times this x dependence. I'm going to highlight the x dependence for you in a different color so you can see it better. Times this x dependence has to be equal to the sum of these other two constant vector values times this x dependence and times this x dependence. So if I write that out in a simplified form, I'm just going to say that the tangential component, which I'm going to write as a big T, little t, times e to the minus j k2x sine theta t is equal to the tangential component of the incident field, e to the minus j k1 x sine theta I, plus the tangential component of the reflected field, e to the minus j k1 sine, forgot the x in there, x sine theta r. And this has to be true for all x values, because that planar interface extends over all the values of x, and this boundary condition has to be true everywhere. The only way for that to be true is if the arguments of these exponents have to be equal. Now, this condition is called phase matching. And this is the reason why Snell's law, as you know it, as you learned it in your physics classes, is actually true. Because what we have is that k2 sine theta t has to be equal to k1 sine theta I, which also has to be equal to k1 sine theta r. All these things have to equal each other. Conceptually, what this looks like is if we draw a picture of the interface again. There's our material interface, here's material 1, here's material 2. Our incident wave is an incident along some angle, and it's got that ki vector. The incident wave phase fronts are perpendicular to that propagation vector, and they look like this. They have a certain spacing. Our reflected wave, coming out this way, has to have phase fronts that are perpendicular to the reflected wave vector, and its phase fronts on the interface have to have the same spacing as the incident wave's phase fronts. I'm going to keep drawing the incident wave a little further out so you have some places where they both exist to look at. There we go. So that means these reflected wave phase fronts kind of look like this. So that where the phase fronts are meeting each other on that interface, the phases are equal. Same thing has to be true about the transmitted wave, even though its propagation vector is coming out at a different angle. What that means is that the spacing between phase fronts for the transmitted wave will be different than the spacing between phase fronts for the incident and reflected wave. And that tends to look something like this. These phase fronts, too, are perpendicular to the direction of propagation for the transmitted wave. But you can see that at all of these points on the interface, these surfaces of constant phase intersect, and they are the same distance apart on the interface. That is the phase matching condition that Snell's law is enforcing. And out of this expression, we can get Snell's law in the way that we are used to seeing it, which is that the incident and reflected angles are equal, and that sine theta t is equal to k1 over k2 times sine theta I. And you might see this k1 over k2 term simplified because k1 over k2 is equal to omega square root mu1 epsilon 1 over omega square root mu2 epsilon 2. And if the mu's are equal because we're talking about dielectrics, and the frequencies are equal because we're only talking about one source over here, you end up with square root of epsilon 1 over square root of epsilon 2, which is how you'd normally see it. So that's Snell's law for you.